Y nuestro próximo profesor, Matthew Stanley, viene de Gallatin, NYU. Él fue condecorado con el Gallatin Dean's Award 2014-2015 por la excelencia en la enseñanza. Este premio fue otorgado por la Universidad de Nueva York. Además, la Fundación Nacional de Ciencias lo reconoce como profesor que busca utilizar las humanidades para mejorar la educación científica en las universidades. Los dejo con su clase, el extraordinario genio Albert Einstein, su vida y su universo. Disfruten.
Thank you for coming back even after the donuts were gone. I'm here to talk about Albert Einstein. The face needs no introduction. I'm going to be talking about the story of his life, and we'll learn about his science along the way. Einstein traced his interest in science to a particular moment in his childhood. He was 5 or 6 years old, and he was sick, so he had to stay home from school. And to cheer him up, his father brought him a compass. And the young Albert was amazed by this, because no matter how you turned the compass, how you moved it, how you looked at it, the needle always pointed the same way. There was this invisible force at work that he had never seen before. And even better, father told him that this was something he could study and understand and learn. And Einstein became focused, perhaps obsessed, with this idea that in the universe around us there are unseen forces that if we ask just the right questions, we can understand their true nature. And it's this kind of childlike questioning that really marks the work that Einstein does throughout his life. This is the first picture we have of him, looking very sharp, I imagine. Einstein was born in Germany to a Jewish family. They moved around a little bit. His father and uncle ran an electrotechnology company, so they were the early adopters of the 1880s. Einstein struggled quite a bit with the kind of education he got in German schools. In particular, he didn't like to be told what to do. So his teachers, as you might imagine, didn't much care for this, and German education at the time was very rigid and disciplined and militaristic, and Einstein hated just about everything, every aspect of that. That said, despite the stories you may have heard, he did fine in school. His grades were pretty good, with the single exception of French, and you can decide for yourself whether that's important. So as Einstein struggled against the kind of education he got in the German school system, this is the young Einstein. He goes to Switzerland for college, where he can get a somewhat more liberal education. And we're not used to seeing Einstein as a young man. Dapper, handsome, gazing off into the distance. One of his friends at the time said that Albert had the kind of beauty that caused chaos at the time. I don't quite see it myself, but it's incontestable that Einstein had a very successful series of relationships with women his entire life. For most of his adult life, he was both married and had a girlfriend or a mistress. At the very end of his life, he was actually dating a Russian spy. So that said, the young Einstein is passionate about physics as well as women. He courts the one woman in his physics class and marries her. That's Mileva Marisch. And as a young man, a young German man, he's a bohemian. And this is a movement in the early 20th century about beauty, peace, and love. You would get together with your friends and read poetry and sing love songs. And this is the young Albert Einstein. And with these same friends, he would sit down and read physics and philosophy and love poetry. Now, the philosophy he would read with his friends was significant. This was not self-help books that he got off the shelf, but rather it's figures like Henri Poincaré, David Hume, and Ernst Mach. These are some of the foremost philosophical thinkers of the age, and they're all distinguished by their willingness to ask hard questions about things that we already think are true. They take a critical approach to received wisdom. So the young Einstein graduates with his physics degree, but he's unable to get a job, not because his grades are bad or because his skills are poor, but because he never used to go to class. So what he would do is with his friend Marcel took excellent notes, so Einstein would not go to class and just read Marcel's notes and then show up the day of the test and do fine. So his grades were very good, but none of his teachers liked him. One of his teachers famously called him a lazy dog because he never showed up to class. So upon graduation, Einstein can't get a job in physics because no one will write him a letter of recommendation. Instead, a family friend gets him a job at the patent office in Switzerland. So his job is to look at patent applications. As people invent new things, they send in an application explaining how it works. And Einstein's job is to figure out whether or not the machine would work and whether or not they should be granted a patent. So by this point, he has a steady job, he's married, he has children, and he's doing physics in his spare time, essentially for fun with his friends after work. And what it meant to do physics around this time, right around 1900, was to study something called the ether. Now, the ether is a scientific category that we don't use anymore. It won't be in any textbook you read in school. But 100 years ago, this is what it meant to do physics. So the ether was this invisible substance that you couldn't touch, but seemed to fill all of space. So the argument for its existence goes like this. You can hear me right now because there's air in between my vocal cords and your ears, and that air supports the waves of sound that carry my voice. So if there wasn't any air, you couldn't hear anything I was saying. Now, it so happens that light is also a wave, so that suggests that if we need air to carry sound waves, we must need some medium to carry light waves as well. So this substance comes to be called the ether. And the ether has to be everywhere. It has to be in between you and me because you can see me. And we can also see distant stars, so it must fill space as well. Now, one of the great contributions of ether physics around the 1870s is to conclude that this ether substance must also carry electricity and magnetism. So this one mysterious substance explains why light travels, how electricity works, how magnetism works, and so on. So if you're a physicist, you're studying the properties of this ether. And in particular, you're studying the way it acts in a specific situation. So you might study the state of the ether inside a radio transmitter or inside an electrical light. But no one quite understood what the ether was or how it could work in a grand sense. And Einstein didn't like this. Einstein preferred, instead of ether physics, a different discipline called the laws of thermodynamics. Now, don't worry at all about what thermodynamics is. What I want you to see is just that you can express them, the whole laws of thermodynamics, in two very short statements. Energy is conserved, entropy increases. And these apply to the universe as a whole. So if you understand what energy is and you understand what entropy is, then you have this grand principle that can help you understand just about anything you encounter. So Einstein thought all of physics should look like this. It should be short, clear statements that help you understand a grand number of things. So Einstein took this approach to the physics of the day, and he wanted to ask these kinds of childlike questions. So for instance, what if I was riding my bike through the ether? What would the ether look like when I was riding my bike very, very fast, say at the speed of light? And this gets him asking certain kinds of questions that other people are not at the time. He publishes these ideas in what nowadays we call the special theory of relativity in a paper in 1905. He's still working as a patent clerk. No one knows who he is. And the paper is pretty much guaranteed to irritate any scientist who reads it. It has no footnotes. It has no citations to existing work. It doesn't connect to the other experiments that people are doing at the day, to the other theories. It's just his particular set of ideas. And his approach is particularly distinct. It's very Einsteinian, and we're going to go through it here so you can get a feel for how Einstein asks questions about the world. So, as I said, this is the theory that comes to be called special relativity, and it's based on two postulates. A postulate is something, a statement you make to start thinking about something. You don't really prove it, you don't demonstrate it, you simply say, let's assume that the world works this way. And the first postulate of special relativity is that the laws of physics are the same in all inertial reference frames. And second, the speed of light is the same in all inertial reference frames. Now, don't panic about inertial reference frame. This is a fancy way of saying either sitting still or coasting at a steady velocity. So you're all in an inertial reference frame right now. And when you get on the train and the train is coasting, you're in an inertial reference frame. So it's either sitting still or coasting. Now, this statement here, in some sense, is so obvious it doesn't require explanation, in that, of course, the laws of physics are the same for everyone. That is, whether you're sitting still or whether you're moving in a train, if you conduct a series of experiments, you'll arrive at the same laws of physics. And again, this seems, no scientist would disagree with this at the time, or today for that matter. But it's so obvious that you wouldn't even need to say it. Why would you even bother? But Einstein says, actually, there are important truths hidden inside this concept that we need to look at closely. And then the second statement, the speed of light, is a similar one in saying that there's no one person who can tell you what the speed of light is. We should all agree on it when we do our experiments. Again, doesn't seem like this should be a big deal. But Einstein combines this with what's called a thought experiment, a Gedanken experiment in German. So a thought experiment is not something you do in the laboratory. There's no equipment that you have to set up for this. It's solely done in your head. So you just take a certain set of ideas and really carefully think through all of their consequences and then see what the result is at the end. So we're going to do that now. We'll get some practice doing thought experiments. Now, there's one missing piece we need to make sense of special relativity, and that's Einstein, one of the books Einstein read as a young bohemian, catching up on his philosophy, and that's the Austrian physicist Ernst Mach. He had a philosophical position called positivism. Now, I should say the word positivism applies to many, many different kinds of things, so don't worry if this isn't what you know as positivism. So Mach said, if you're a positivist, you should do science only thinking about measurement. That is, a scientific category, something like the ether or gravity, is only meaningful insofar as you can tell me how I can measure it. That's what it all comes down to. Again, seems fairly unproblematic, but turns out to have deeper consequences that are quite significant. So Einstein, in his paper of 1905, wants to take this positivist approach to physics and apply it to our basic categories of the universe, space and time. That is the very way we think about things being arranged around us and the way we think about time passing. And he comes up with something called a light clock. So a clock can be anything that has a regularly repeated phenomenon. So if you think of the old-style pendulum clocks, the repeated phenomena is the pendulum going back and forth. The digital clock you have on your arm or in your pocket, there's a little crystal that's vibrating in a very specific way. So you can make a clock out of anything that's regular. So Einstein says, let's make it out of two mirrors. So I've got a mirror here and a mirror here, and then a light bulb down at the bottom of one of these, and the light bulb flashes and lets a pulse of light go, and it goes up and hits the mirror and then comes back down again. And when the light completes that one circuit, we call that 1 second. Okay, we're going to build our clock, so one complete movement of the light pulse is 1 second. So why would you start thinking about these things, you might say? And it's because Einstein was reading Ernst Mach. So Mach said it's all about measurement. So Einstein said, well, then if I want to talk about time, how do I measure time? So Einstein says, because he's a positivist, time is just the ticking of a clock, because that's how you measure time. So it's not the sense of time passing. It's not some kind of cosmological property that's true for everywhere and everything, but rather, when I say time, I mean the clock I'm holding in my hand. So Einstein specifies this particular kind of clock so he can do a thought experiment about time. So all is well, right? We've got our light clock running. Here, the light pulse goes up and down, tick, tick, tick. Now, it only gets strange when all of us have light clocks. So if everyone could please get a light clock. So you've got the two mirrors in front of you, and imagine the light bulb on the bottom one, and watch the flash of light, and it goes bink, and the light comes up, hits the top mirror, and comes back down and hits the bottom one. And that's 1 second. Okay? Everyone's light clock working okay? All right, so now we're going to synchronize our light clocks. So all of our clocks tick at the same time. All right, so watch my clock and watch yours and make sure they're going at the same time. Right, so we're on the left here right now. So everything is fine until I start moving. Now, when I start moving, you're watching the light pulse go straight up and down in front of you. But when you watch my light pulse, here, let me get over here so I'm the right way for the diagram. When you watch my light pulse, it seems to be going to the side because it has to go at that angle so it completes. Now, from my point of view, it's still going up and down. It's your clocks that look like they're going to the side. Now, if you watch the diagram very carefully, something important happens, is that your light clock finishes ticking before mine does. So Einstein says, my clock is running slow compared to yours. And I say, your clock is running slow compared to mine. And since we're positivists, time is just the ticking of a clock. So by moving, I am now changing the way time passes between the two of us. We say that time is relative between you and me. Now, your normal instinct when you hear about this is to say one of us is right and one of us is wrong, right? Which of us has the correct clock? But you'll remember that the postulate of special relativity says that all inertial reference frames are equal. We're both the same. None of us are privileged. No one of us can say we're right and the other one is wrong. So the conclusion, quite perversely, is that time changes depending on how you move. And this phenomena is called time dilation. Don't panic about the equation there. I really just want you to see this curve. So the amount of time dilation, that is the amount by which our clocks differ, is a function of the speed of light. And you have to be going very, very close to the speed of light before you notice this happen. And this is why you don't notice this happening when you're on the metro, or you shouldn't. Anyway. So the speed of light is extremely fast. It's 300 million meters per second. Okay? So that's so fast that the fastest human-built object is still here. Okay? So there's no way you would notice this phenomenon just in your daily life. It's only when you get going very, very close to the speed of light that you would see this phenomenon happen. So that's why Einstein can explain why no one had ever noticed this before. Now, so that's how you do a thought experiment. So Einstein does a thought experiment like that with clocks, and then he does a thought experiment, and then one of the consequences, these are my daughters, Maya and Zoe. Now, if Einstein is right about time dilation, you get something called the twin paradox. So identical twins are the same age, by definition, right? So they were born at the same time, they are the same age, but if Zoe gets on a spacecraft, and the spacecraft zooms around close to the speed of light, her clock, her aging is a kind of clock, and Maya's aging is a kind of clock. Their clocks used to be synchronized, but as Zoe gets close to the speed of light, her clock slows down. A year for Maya is not a year for Zoe anymore. So when Zoe comes back to Earth and they meet up, Maya is now older. This is a clear consequence of Einstein's idea about time, and it seems absurd, This can't be true, right? It is we call it a twin paradox. We actually have clocks nowadays that are accurate enough that we can do this experiment, and in fact, twin clocks do age differently. Another consequence of this, whoops, wrong piece, is called the relativity of simultaneity. And we don't need to go through the details, but it's the same kind of inquiry we did with the light clock. And what it means is that two people can disagree about whether something happens at the same time or not. So I might have said, I started my lecture right on time. And then Sophia says, no, you didn't. And in fact, if she was going close to the speed of light, we would disagree about that fundamentally, and there would be no way to resolve that. So Einstein goes on to do the same, not only with measuring time, but with measuring distance, with space. So the equivalent effect is called length contraction. So in the same way that my clock slows down as I move faster and faster, you also see the meter stick I use for measuring things shrink and get compressed. Just like with time dilation, length contraction doesn't happen until you get very, very close to the speed of light. So again, you can't notice it on a regular basis. And then there's a third phenomenon that comes along with this called mass dilation. So again, it's very sensitive to the speed of light. And what it means is that, so as I'm zooming across the stage near the speed of light, and you're watching my clock tick, and you're seeing my meter stick shrink, you're also taking measurements of my mass, how much I weigh, which may not be polite, but there you are. And you notice that as I get closer to the speed of light, my mass increases quite dramatically. I become more and more massive as I go faster and faster and faster. And one of the consequences of this is that as I get close to the speed of light, my mass increases so much that I can never go a little bit faster. And that's how I can never get faster than the speed of light, as David was talking about this morning. Now, the mass dilation formula yields something interesting, which is this. Probably the most famous equation in the world, and the only one I won't apologize for having up here. E equals mc squared. Energy is equal to mass times the speed of light squared. The c squared is just a number. You can ignore that. Rather, this is simply saying that energy and matter are, in some sense, the same. They share some nature. One can be converted into the other. So by the end of Einstein's 1905 year, he's done some extraordinary things. Special relativity has given us this world where clocks run slow, things shrink, matter and energy can convert one to the other. But he has the question that a scientist will always ask is, why should I believe you? You have this weird idea. How can I check to see if it's right? And Einstein doesn't have any of that in 1905. The best he can do is say that his theory is compatible with experiments that have already been done, but there's no way to test it. In particular, it's compatible with an experiment called the Michelson-Morley experiment, which was supposed to detect the motion of the ether. Remember that basic fundamental element of physics of the day. And the Michelson-Morley experiment always resulted in a negative result. It would never explain, it could never detect the motion of the ether. And Einstein, again, as a positivist, says if I can't measure it, it's not real. So he says if you can't measure the motion of the ether, then it is superfluous. That is, he's not saying it's wrong. He's not saying it's not true, but rather we simply do not need this thing anymore. So if you can imagine this 26-year-old patent clerk, never having held an academic job, never having had a scientific position, coming out and declaring the fundamental basis of all of the science of his day as superfluous. That's the kind of guy Einstein was. This is actually only one of a few topics he tackles during 1905. This is sometimes called his miracle year, where he has this incredible series of papers that revolutionized the way we think about the world in several different ways. So we've got special relativity that we've been talking about, the photoelectric effect, which gives rise to quantum mechanics, which I'll talk about in a bit. And then these two are actually the ones that get everyone's attention, is Einstein provides, for the very first time, a way to detect the motion of molecules, to show that atoms are real. Now, this seems so different than the way we think about the world today that it takes a moment of reflection. 100 years ago, it was totally reasonable to not believe in atoms. You couldn't see them. You couldn't interact with them directly. It was totally fine to say, I really don't believe that atoms are out there. And what Einstein is able to do is finally give a way for people to see that atoms are certainly real and that they can be manipulated. So that's what gets people's attention. Special relativity, which he really cared about, was not of much interest to anybody. So Einstein finally gets some academic jobs out of this. He goes from Prague back to Switzerland and then on to Berlin, where he becomes the head of the Kaiser Wilhelm Institute for Theoretical Physics. Now, while he's working on all of these things, this is 1912 when he finally gets to here, he's not the only person working on relativity. In fact, one of his old math teachers from college sees Einstein's papers in 1905 and is amazed. This is the one who called him a lazy dog. So he says, I can't believe that this lazy dog Einstein produced a theory like this. So Minkowski is very excited about relativity, but he doesn't like the relative parts of relativity. By which I mean, he doesn't like the fact that you and I can disagree about things like space and time. That doesn't seem like the kind of universe he wants to have. So he finds an analogy inside special relativity to something in geometry. So if you think back to high school geometry, the distance between 2 points, say the length of something, is a combination of an object's size in 3 dimensions, say left and right, up and down, front and back. And the combination of all of those gives you the length of the object. And you and I might disagree about whether it's left or right, or if I lay on my side, my left and right is now your up and down. So we'll disagree about the x and the z, but we'll always agree about the L. So Minkowski noticed that inside special relativity, there is something like that. There's something that is absolutely true between observers that we will all agree on. And he calls it the interval. And don't worry about the equation, but you can see the difference here immediately is that Minkowski has tacked on this extra term, t squared, time. So Minkowski says, we might disagree about our measurements of space and our measurements of time, but we will always agree about the combination of our measurements of a new thing called space-time. Minkowski wants to say that hidden inside relativity is this claim that the world is actually 4-dimensional, that time is just one more dimension of space, and that we should really measure our existence in the universe by this new idea, by space-time. So the analogy goes kind of like this. If you look at a map, you've got north, south, east, and west, and if I'm going northeast, I'm going a little bit north and a little bit east. And if I change my trajectory a little bit, now I'm going more north and less east, or I might go more east and less north. So our direction through space is a combination of those 2 directions. So Minkowski says that's how it is with space and time. So our natural existence, right now, you are all moving through space-time in a natural way, which is some combination of space and time. And then as you speed up, get closer towards the speed of light, you'll experience less time and more space. So you're changing your trajectory through the 4-dimensional universe of space-time. This is extremely strange. Your brain cannot visualize 4 dimensions. We are not built that way. You'll have to ask Heather why. But Minkowski was not shy about pointing out the philosophical consequences of this idea. He says these ideas are radical. Space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the 2 will preserve an independent reality. And this is really an extraordinary claim. I want to make sure we are all on the same page about this. Is he's saying that the way you experience the universe, a universe of space and time, is wrong. Rather, the universe is this 4-dimensional compound of space and time, and we see it incorrectly. We're like a worm eating our way through the apple. We don't actually see the surface of the thing we're traveling underneath. So this notion that we imperfectly see the universe, that we see it incorrectly, is of course a very old idea. If you've read Plato, this is his myth of the cave, with the idea that we only see literal shadows. That's where Minkowski is talking about. Now Einstein reads this and he hates it. Space-time seems exactly like the kind of thing he was trying to get rid of. It's another abstract idea that you can't see directly, that you can't measure directly. So Einstein says, I'm just going to do it on my own. That is, I'll make relativity better. And in particular, he tries to create what he calls general relativity. So far we've had special relativity, which only applies when we're coasting or sitting still. And general relativity should apply to anyone, no matter how they're moving. All right? So it's general in that sense. And Einstein's insight about this, which he calls the happiest thought of my life, comes from a realization he has. And I don't know why he's thinking about this, but he's thinking about what it would feel like to fall off the top of a building. And his reasoning goes, actually, we can kind of do this too. How do you know that gravity is pulling on you right now? Take a minute and feel it. Where do you feel gravity on you? Sorry, I don't know. I don't know the Spanish for these words. Where do you feel it? Anybody? You feel it, that's right, so someone's pointing to their chair. That's exactly right. What you feel right now is your chair pushing you up against gravity. Okay? So you actually know gravity is pulling on you, not because you feel a sensation of being pulled down, but rather because the chair is pushing you up. And then the next step in this thought experiment is, what happens if we pull the chair out from underneath you? What do you feel? For a moment, nothing. So Einstein's insight is that a freely falling person will not feel their own weight. And this doesn't, as always the case with Einstein, it's not obvious why this is so important at the moment until you run it through another thought experiment. But he calls this the equivalence principle. And his claim is that acceleration is indistinguishable from gravity. That is, you cannot tell them apart in a scientific way. So his thought experiment goes like this. I should say, thought experiments in relativity are very strange. So this scientist wakes up locked in a box. There's no windows. She can't see out. All she has is a ball with which she can perform some experiments. I don't have a ball, so I'll use this. So she takes the ball and she drops it, and as expected, it falls down. And one way to interpret that result is that the room she's locked in is sitting on the surface of the Earth, and the Earth's gravity is pulling it down. That's probably the interpretation all of you naturally had. But, Einstein says, there's another way to think about this. If that box is not on the surface of the Earth, but out in the middle of space with no gravitational field, but it's strapped to a rocket, and the rocket is pushing upwards, this time, when she drops the ball doesn't go anywhere, it stays where it is, but the floor of the box moves upward. So now I'm going to drop it again, and you need to change your brain. So instead of seeing the marker fall, you're seeing the floor come up. Anyone able to do it? It's not easy, but Einstein's point is that you can't tell the difference between these two situations if you're the scientist locked in the box. So gravity is indistinguishable from acceleration. And this is the key thought that lets him figure out how to generalize relativity into a new kind of way. So here's another consequence of that same thought experiment. A little faint, but hopefully you can see. So I'm locked in the box, but this time I have a friend. And my friend is going to shine a laser in a little hole on the side of my box. Okay? And if the box is just sitting in deep space and not doing anything interesting, the laser beam just goes straight across and hits the far side of my box. All good so far? Now, we're going to turn on the rocket ship. So the floor is now accelerating up. So as the laser beam comes in, the floor comes upward, and the laser beam hits low on the far wall. So from my point of view, the laser beam seems to have curved. And if the equivalence principle is correct, that gravity and acceleration are indistinguishable, then gravity must bend light as well. Right? So I want to emphasize here, this is not an experiment Einstein does in the laboratory. There are no sealed boxes and laser beams in 1912 when he's doing this. This is just something he thinks through in his head. But this is now something you could go check. So Einstein wants to combine the equivalence principle, this idea that acceleration and gravity are the same, with an idea called covariance, which is simply that the laws of nature look the same to everyone, everywhere, no matter what. So it's just special relativity bulked up on steroids. Now, Einstein spends years trying to figure out, what he has to do is find a series of equations that can give him both special relativity and the equivalence principle and covariance. And he fails again and again and again. And finally, he realizes that what he needs to do is use Minkowski's four-dimensional space-time idea. And once he does that, then things begin to fall along much easier. And the idea he then comes up with is that space-time is not just a uniform thing in the universe that we experience, but rather that it can be bent and warped and shaped, particularly by gravity and mass. So the Earth's gravity actually deforms the space-time around it and changes our experience of the world. Now, the physics of general relativity is very simple. Every object moves in a line called a geodesic. Okay? And a geodesic is a straight line. So the claim of general relativity is that everything in the universe moves in a straight line. Fine. The problem, you might say, is that, well, but I know that the Earth goes around the sun, and that's not a straight line, so how can that be? And Einstein says, actually, it is a straight line in 4 dimensions. It's just our experience of it that it looks like a circle in 3 dimensions. And you're probably, if you've done any long flights, you're already familiar with this idea that, say, a straight line between New York and Moscow on the globe is a straight line and the shortest possible line. But when you project it onto the screen on the back of your seat, it looks like it's curved. And that's just because that's what happens when you take a 3-dimensional shape and turn it into a 2-dimensional one. Similarly, the physics of the universe are written in 4 dimensions, but we experience it in 3. So what Einstein eventually comes up with in 1915 is what's called the Einstein equation. And it's typically called one of the most beautiful equations of all time. So this here, you can ignore. It's just a number. This is the curvature of space-time. We say g mu nu. This is mass and energy and how much there is. And we say t mu nu. So we say here that the curvature of space-time is caused by the presence of matter and energy. A equals B. It's as simple as an equation can get if you're already familiar with 4-dimensional mathematics. If you're not, this beautiful equation turns into this. So it's actually 128 separate little equations all packed together in this particularly efficient way. So general relativity is very difficult to use mathematically. The math is very challenging. So by 1915, Einstein finally has what he really needs, which is a way to tell whether or not his ideas are right. So there are the so-called 3 classical tests of general relativity. The first one is the idea that gravity bends light. We already did a thought experiment for this one, but this phenomenon is very tiny. So if you were to see it in the real world, you would need to wait for a star to be right near the edge of the sun, and then the star would be slightly displaced by the sun's gravity and appear to be in a different place. You can only do this at a solar eclipse, very difficult to do. The second test is called the precession of the perihelion of Mercury. And it is essentially an observation that Mercury's orbit has a little wobble in it. And this had been known for a long time. Einstein is able to explain why the wobble is there, but he creates his theory knowing that he has to explain this, so it's not quite so impressive. The third is what's called the gravitational redshift, which is that colors should look slightly redder as they come out of a gravitational field. This is an intensely difficult experiment. It actually isn't done until the 1960s. So this is off the table because it's not technically feasible at the time. This is off the table because it's not very persuasive. So he's left with this prediction that gravity should bend light. So this is late 1915. Einstein finishes his masterpiece of general relativity, and no one knows about it. And the reason for that is it's the middle of World War I in Europe. So after the beginning of World War I, scientists on both sides of the fighting become intensely patriotic. They refuse to send scientific papers back and forth. They refuse to share ideas. At one point, German scientists refused to use English words in their publications. It's really quite extraordinary. So Einstein is completely isolated in 1915, and no one knows about his theory. The exception to that is this group of his friends. So these three are physicists and astronomers in the Netherlands. And the Netherlands are neutral during the war. So Einstein is able to go from Berlin to the Netherlands to teach them about general relativity. And then since the Netherlands are neutral, this guy, Wilhelm de Sitter, sends a letter about general relativity to this guy in England on the other side of the fighting. This guy is named Arthur Eddington. He's a British astronomer. And quite amazingly, he's one of the very few people in Britain who would even read a German theory. It sounds like exaggeration, but I swear it's not. British scientists refuse to read German science, except for Eddington. And the reason for that is that Eddington was a Quaker, and therefore a pacifist, and thought the whole war was a really stupid thing. And he thought it was great, this idea that English and German scientists could work together on this project. So Eddington devotes the next few years of his life to observing the gravitational deflection of light. That is, he actually goes out during a solar eclipse to an island off the coast of Africa and measures the motion of the stars caused by the general relativistic effects. And this is extraordinary because Einstein really doesn't know this is even happening. Einstein is still secluded in Germany behind the trenches. So Eddington does all of this on his own. And on November 6th, 1919, Einstein wakes up and discovers he's the most famous scientist in the world. And this is largely because Eddington was very good at talking to the press. He communicated with journalists. He set everything up in advance. So we get these tremendous claims. Lights askew in the heavens. Einstein theory triumphs. No more than 12 people in the world can understand it. So Einstein, literally overnight, goes from being an obscure German academic to the most famous and recognizable scientist in the world. It's just a couple years after this that he gets the Nobel Prize. Now, interestingly, he doesn't get the Nobel Prize for relativity. He gets it for the photoelectric effect, which I'll talk about in a moment. He doesn't get the money for the Nobel Prize either, because he has to give it to his wife as part of the divorce agreement. So the photoelectric effect is an obscure thing that I won't go into too much, but basically there's certain circumstances under which when you shine light on metal, electrons are ejected. It's a fairly obscure laboratory phenomenon, but Einstein is able to explain it in a way no one had really thought about before. And his claim is this, that on the level of single atoms, single electrons, energy works differently. We're used to thinking about energy as being something like water. You can pour as much or as little water in to a glass as you want. And that's how we're used to thinking about energy. I can put as much or as little as I want. But on the atomic scale, energy behaves like ice cubes. You can only put a certain number of ice cubes into a glass. You can put in half an ice cube, but then it's just an ice cube that's smaller. So the idea that energy travels in these packets of energy comes to be called quanta and gives rise to quantum physics. It was one of the great disciplines of science of the 20th century. It's actually not Einstein who runs with this idea, but rather this Danish guy named Niels Bohr. He creates a whole new model of the atom based on this, and that's the model of the atom that you're familiar with, the sort of planetary model. That's the Bohr atom. Bohr gets the Nobel Prize for that. He uses his Nobel Prize money to put a pipeline of beer into his laboratory. And his laboratory becomes the place where quantum physics is invented. People like Werner Heisenberg, Ernst Schrödinger come and study with him. And quantum physics becomes one of the most successful theories of all time. It's intensely good at predicting exactly what you will see as the result of a particular experiment. And that's great. The problem is that there are things you have to give up in order to get these predictions. So quantum physics is uncertain in the sense that you can never have all the information you might want about a system. It's acausal. You can't explain why something happens. It's indeterministic. If you set up exactly the same circumstance twice, you might get a different result. And worst of all, to Einstein, it's observer dependent, meaning that if I'm looking at the experiment, I'll get a different result than if I'm not looking at it. And Einstein thinks all of this is absurd. He says the universe simply cannot function in this way. This is not what he is looking for. So thus begins one of the great intellectual debates of the 20th century between Einstein and Bohr about the nature of the universe. Bohr says quantum physics is the essential truth about reality, that it is uncertain and confusing and statistical, and Einstein says that can't be. The whole point of science is to find the truth, the great objective absolute truth that's out there. And their particular disagreement, I said, is about whether the universe is inherently random, and Einstein would famously say, God does not play dice, to which Bohr would reply, stop telling God what to do. These arguments go back and forth for a good 10, 15 years. They're never really resolved within their lifetime. But by the 1930s, Einstein is not just the most famous scientist in the world, but he is an icon. He is an instantly recognizable person. You take a picture of him in his bathing robe on the beach. You take a picture of him when he's hanging out with Charlie Chaplin. And wherever he goes, ridiculous pictures get taken. Because he's Albert Einstein. That's him holding a doll of himself. And because he is supposed to be the smartest person in the world, people ask him about everything. Professor Einstein, what do you think about modern art? Professor Einstein, what do you think about jazz? And he would gamely reply, say, well, I think this, and I think this. And one of these times, a reporter had heard about his exchange with Bohr, about God playing dice, and says, Professor Einstein, do you believe in God? And Einstein says, yep. And then kind of goes about his business. And then it's front page of the New York Times, Einstein believes in God. So Einstein's friends write to him and say, is that right? I didn't realize this was something you cared about. And Einstein says, well, yes, I believe in God, but not in the way that everybody means. What he means is he doesn't believe in an anthropomorphic entity that sits up there in heaven and makes decisions for the world, but rather he prefers Spinoza, the 17th century Jewish philosopher, his version of God, in which God is actually the orderliness of the universe. The very rationality and comprehensibility of the universe is what Einstein means by God. So when Einstein says, I believe in God, he means, I believe that you can understand the universe. This matches up with another important part of Einstein's identity, which is that Einstein was Jewish. Interestingly, Einstein does not think of himself as Jewish until certain political and social events force him to do so. So he grows up in a completely secular family, and it isn't until in between the two world wars in Germany that Germany has a tremendous economic collapse. So it gives rise to tremendous economic and political chaos that eventually give rise to the Nazis seizing power in 1933. And the Nazis were anti-Semitic, that is, anti-Jewish, explicitly as part of their government policy. So people like Einstein, who were Jewish by blood, by family, but not Jewish by practice, suddenly found themselves being called Jewish. And Einstein was very perturbed by this because he never went to a synagogue, he never learned any Hebrew, he never had a bar mitzvah. There's nothing about Jewish practice that Einstein ever did. But nonetheless, he suddenly found himself the target of anti-Semitic attacks from all across Germany. In fact, there's a special sub-branch of physics called Deutsche Physik, German physics, that was devoted to attacking Einstein and relativity as being un-Aryan science, that is, as being Jewish science. And the people involved, Leonard and Stark, these are Nobel Prize winners. These are serious physicists. And Einstein quickly realizes that Germany is going to be a dangerous place for him as a Jew to stay. This is actually when he becomes a Zionist as well, because once he realizes he's part of a group of people that are under attack, that are in danger, he decides that he and his comrades need a safe place to go. So he's interested in Zionism not out of any sense of an eternal homeland for the Jews. He just wants a place where he and his friends can be safe. So this all comes to a head in 1935. The Nuremberg laws in Germany make it illegal for anyone with a quarter Jewish heritage to hold a government job, and all professorships were government jobs. So Einstein is thrown out of his job, his house is ransacked, and he flees to the United States, where a group of wealthy philanthropists in New Jersey set up a place called the Institute for Advanced Study, which you can still now go and visit. And Einstein settles in there with his family as a refugee. And Einstein is very happy to finally have a place where he can just work quietly and not be bothered. This changes with the development as World War II comes into full force. So by this point, the United States and Mexico, I should say, have large numbers of refugee scientists from Germany and Austria living there who have fled from the Nazis. But enough physicists stayed behind that people like Einstein realized that it's possible that the Nazis could build an atomic bomb, which he's terrified by the prospect of. So even though Einstein is a lifelong pacifist and internationalist, he writes a letter to the President of the United States telling him about the possibility of an atomic bomb and asking that a project be started in order to build such a bomb before the Nazis. Now, interestingly, as we know, the project is successful. It's the so-called Manhattan Project. Einstein is not able to work on the Manhattan Project because his politics are too left-wing. That is, they suspect he might be a communist, so they don't let him in. Nonetheless, after the war, Einstein's work becomes deeply associated with the bomb. In particular, his famous equation, E equals mc squared. And if you can imagine what it must be like for this mild-mannered pacifist to see his life's work, his great intellectual achievement, literally stamped on the mushroom cloud of death and destruction. He's deeply disturbed by this. Like many physicists after the end of World War II, he's concerned. He devotes himself to various causes of international government, trying to set up what eventually becomes the United Nations, trying to remove nuclear weapons from the world. And while he does that with his name. He doesn't really leave New Jersey anymore. He just hangs out. And instead, what he wants to do is finish physics. And what I mean by this is he wants to create something called a unified field theory. This is still his argument between Bohr and himself about whether quantum mechanics or general relativity is more correct. So he can't deny that quantum mechanics is very good at predicting phenomena in the laboratory. So he has to come up with a way of explaining why that seems to work, even though he wants general relativity to be the deeper truth about the universe. So he works with two of his students named Podolsky and Rosen, and they come up with a thought experiment to test for what's called hidden variables. So quantum mechanics looks messy and random and statistical, like God is throwing dice. So Einstein says, maybe underneath that, there is some orderly nature to the universe, and we're just confused by this kind of cover of randomness. So he calls this hidden orderliness hidden variables. That is literally the truth is hidden underneath what we can see from quantum mechanics. So he comes up with a thought experiment by which you could test this. It actually isn't able to be tested until the 1960s when an Irish physicist named John Bell comes up with a way to do it in the lab. So this is typically called Bell's theorem today because he's the one who figures out how to do it. We're not going to do the details, but it goes like this. If Einstein is right and the world has a hidden order underneath the craziness of quantum mechanics, then the result of the experiment is X. If the world is genuinely weird, if Bohr is right and Einstein is wrong, the result will be Y. So they can finally put this to the test, and the results are Y. And they do it again, and it's Y. And they do it again, and Y. This is done every few years or so now. Someone will do this again, and you'll see the headline in the paper, Einstein proved wrong, and so on. So it's clear that Einstein's vision that there is this hidden meaning underneath quantum mechanics is wrong. He was defeated in that idea. But Einstein's dream of a unified physics, one equation that can explain everything about the world, still stays with us. And every time you see something in the paper about a grand unified theory, or string theory, or quantum gravity, these are all attempts to finish Einstein's project, to find the true nature of the universe in which everything looks crazy, but underneath it is some kind of comprehensible truth. And it's still the same kind of childlike questions that got Einstein started in the first place. Thank you for your time.